Okay, let's begin. Question on the homework.
19.
12.1. What did that say?
The integral of v, and in parentheses is v plus v, the double integral.
Double integral?
Of v, and in parentheses is u plus v squared.
U plus v all squared?
Yeah, no, the v squared, and that's to the fourth.
And this is to the fourth?
Yeah, and it's of du dv. And the boundary of the u is 1, 0. Okay, they're both 1, 0. They're both 0, 1.
0, 1?
Yeah. 0, 1.
And also 0, 1?
Yeah.
Okay. Alright, so how do we do this one? Yep. U substitution? Sure. Well, like a T substitution or whatever. Anyway, so you'd substitute inside here, and then what's going to happen? Basically, that's going to happen, right? And then, what do we get here? What does it become now? Come again?
Oh, sorry.
V over 5, 1 plus v squared to the fifth, minus v over 5 times e to the 10. Okay, so this is v over 5, 1 plus v squared to the fifth, minus v to the 11 over 5 dv. How do I integrate this? Alright, it's going to be u sub, what's going to be the result? Basically 1/10, 1 plus v squared. We're going to add 6 and divide by 6, so this will end up being 60. This is a 5. Right? That's what we're going to get. And then minus v to the 12 over 5 times 12 is also 60. And now we just plug in the limits. So plug in 1 for v. So we get 2 to the 6 minus 1 to 6. Other questions?
23.
Yeah. So technically here, I use the substitution. Or we wouldn't call it U substitution, we'd substitute something else like T. And also to do this part here, I did a substitution. But they're the kind you don't really have to write down the substitution. They're easy enough to do in your head, so you just do that. Yeah. The other one?
23. Double integral of x sine x plus y.
X sine
X plus y.
x plus y inside the angle.
dy dx. And 0 to pi over 3. And 0 to pi over 6.
Okay. How do we do that one? Minus x cosine x plus y between 0 and pi over 3. Now what does that become? minus x minus becomes plus x cosine x. So you integrate this. How would you integrate this one? So we can do by parts. I would probably use a trig identity and avoid by parts, but you could also do by parts. You remember what this guy is? This guy is cosine x cosine pi over 3 minus sine x sine pi over 3. Seems like we can't escape the by parts because we're going to get one here. Okay. I was seeing like this x cosine x would kill that one. Never mind. So I'd sort of write this as this thing. Or do by parts one at a time. So if you have this guy, how do you integrate that?
You do a tabular method?
The what?
Tabular method?
You could do tabular method. So because this actually dies upon repeated differentiation, so I differentiate x, I get 1, differentiate 1, I get 0, plus sign is here, minus sign is here. Integrate cosine, I get what?
Sin x.
Positive sign, right? Don't mess up the signs.
Negative cosine.
Negative cosine. So then you multiply it along this diagonal. Right? So here I would have x sine x, and it takes a positive sign. Here I would have cosine x. It's minus cosine x, but it takes a negative sign. And so I can do the integrals here. The plus pi over 3 is not going to matter, right? Because you do a u substitution, it's going to die anyway. So you just sort of bring the angle with you. And then this is, of course, a negative. So this is minus x sine of x plus pi over 3 minus cosine x plus pi over 3 plus x sine x plus cosine x. Between 0 and pi over 3. Right? And so now we just plug in the limits. So this is minus pi over 3 sine of 2 pi over 3 minus cosine of 2 pi over 3 plus pi over 3 sine of pi over 3 plus cosine of pi over 3 minus, now I'm going to plug in 0, that's going to die. This is just going to give me plus cosine pi over 3. That's going to be 0, that's going to be minus cosine 0. And so what do we have here? Minus pi over 3. Sine of 2 pi over 3 is what? Sine of 2 pi over 3. You guys are taking too long. Cosine of 2 pi over 3. It's negative 1/2, so the negative here makes this positive 1/2. Plus, well, sine of 2 pi over 3 and sine of pi over 3, those are actually the same thing, right? So those will die. Don't have to worry about that. So far I just have 1/2. Cosine of pi over 3. It's also a half. And I have 2 of those, so that's just 1. Well, let me just write it up. Plus a half minus 1. So basically the answer should be a half. Oh, yeah? Is there a sign off? Power 6. We should have been plugging in Power 6. That was a problem. This should actually be a Power 6. That's going to change everything. It wasn't pi over 3. Okay. Start over. So now this is minus pi over 6 sine. Pi over 6 plus pi over 3 is what? Pi over 2 minus cosine pi over 2 plus pi over 6 sine pi over 2 plus cosine pi over 6 minus, that will be 0. This will be plus cosine pi over 3. That will be 0. That will be minus cosine 0. Okay, now we should get that. There's pi over 6 on the other side. Sine of pi over 2 is 1. These are all going to be 1, so that's not going to make a difference. It's going to be minus pi over 6. Cosine of pi over 2? 0. This will be plus pi over 6. Cosine of pi over 6? What? You said square root 3 over 2. Okay, I thought you said something else. Square root 3 over 2. Cosine of pi over 3. Cosine of 0 is 1. So, what is that up to? Radical 3 over 2 minus a half.
That's all right. Don't do it.
But you plugged in, it's right, it's the only thing wrong is to plug in somewhere.
Where, right here, I plugged in pi over 6 here and here. That gives me this.
For the second x sine x, where did you plug that in? So you plugged in pi over 2 instead of pi over 6 there. So you should have said sine of pi over 6, which is 1/2, so it's pi over 12.
You mean this one?
Yeah.
X, pi over 6.
So that becomes pi over 12, and then it doesn't cancel out. And
Okay, so this here is pi over 12, you're saying.
yeah.
Which means this becomes, that won't cancel out.
Yeah, that becomes 2 pi over 12, or negative pi over 6, which then becomes negative pi over 12.
Negative pi over 12 plus radical of 3 over 2 minus a half.
Yeah, that's it.
Okay. Jeez, let's plug it in. Okay. How much time do we have? Any more problems? Okay, last one. What's this say? Are there all where they just give you the limits? Well, I mean, in this, it doesn't even matter in this section. The rectangles, the limits are easy to come up. 12.2 is going to be a little bit harder. Anyway, yeah, what's this?
27 is a draw.
Yeah.
It's a draw. Sketch the solid whose volume is given by blah. Okay, ideas? Yeah, but what are we going to be sketching on this?
You're sketching the plane that
It's going to be a plane, right? We're actually sketching z equals 4 minus x minus 2y, which I can write as x plus 2y plus z equals 4. What does the sketch of that guy look like?
You have to block out the two variables and then
Okay, so my x is going to be
4,
4, my y will be
2,
2, my z will be
4.
also 4. So that's this guy. But I don't want the whole thing in the first quadrant. I just want the part that's above this guy here. So this means our solid. So now I'm on 0 to 1 on the x, so 0 to 1, 0 to 1 on the y. Right? So it's like I'm only drawing the part that's above this little rectangle here. Right? That's projected upwards. And then the plane is going to slice along the top. So it's going to end up looking like where this is going to cut at 4. And this surface here, this is actually the plane z is equal to 4 minus x minus 2y. So that integral, if we compute it, we're actually finding the volume of this solid here. Above the xy plane, above the rectangle 0, 1, 0, 1, that's projected up, and the roof is given by the plane z equals blah. Right? Pretty soon, what we're going to do is I'm going to be describing this to you, and you're going to have to figure out that. Right? You're going to have to go the other way. Like I'm going to say, oh, there's an object created by the plane y equals 1, the plane x equals 1, and bounded above by z equals blah. You should be able to draw this and then come up with that. I'm serious. I'm not even joking. Yeah, so I could say that. I could say a question could be something like find the volume of the solid bounded by the planes x equals 0, x equals 1, y equals 0, y equals 1, z equals 4 minus x minus 2y above the xy plane. Right? Like that could be a question. You reading this would draw this and then come up with that. Right? You're often required to go backwards. Right? But you should be able to read this and figure out this is what I'm talking about. Right? So this is the plane y equals 1. This is the plane x equals 1. X equals 0 is the yz plane. Y equals 0 is the xz plane. This is the plane z equals this minus 4. Above the xy plane means I'm above z equals 0. So that tells me that the bottom is in the xy plane. And then I want everything in between them. So last time we were talking about 12.2, setting up the mechanics of double integrals. I sort of gave you the down and dirty, but now we're going to make things a little bit more specific, and we can talk more about how we're going to be thinking about things. It's all about bounds, right? Bounded by is a phrase you're going to see very often, right? It's all about bounds. You need to know what's bounding my object on the left, on the right, on the top, on the bottom. And then you have to talk about dimension, right? You have to choose who's going to be the constants, who's going to be the functions, who's going to be the surfaces, who's going to be in the 0 dimension, the 1 dimension, the 2 dimension, etc. Right? So let's do this a little bit specific. here, and let a go between constants, and my y can go between two functions. Your book calls this a type 1 region. I don't care what the name is, and you shouldn't care either. Just recognize when you're given something like this. So things like this would look like, in a picture form, they could look something like this. You have one curve up here, g of 2 of x. You have another curve doing something here, y equals g1 of x. And my x can be given between limits a and b. You project it up. So my region D can be described this way. Notice that in particular, I can look at my region D and I can describe it as there's a top curve and a bottom curve. Right? Once you can see that there are two functions, that clearly there's one function on the top, there's another function on the bottom, we have this kind of region. It might also look something like, this would be the case where you're just given the xy limits because it doesn't bound itself, but it could also be that the functions themselves provide the bounds. Right? So I can say bounded between these two curves, in which case you have to find the intersection. That will be the A. The intersection here, that will be the B. This can be my region D. This will be g1 of x. This will be g2 of x. Well, here I'm using g2 to be the top function, so it's the other way around. It's g1, that's g2, right? Because this curve, as you can see, is the top, right? The other curve here is the bottom. Right? So you can do that. So clearly here you can see that this guy is the top curve, that guy is the bottom curve. It's very important that you should be able to identify top and bottom, left and right. A, according to the x-axis, is the left constant. B is the right constant. Right? So here I'm thinking of x and constants. I have to figure out who's the left, who's the right. And if I'm thinking of y as functions, as curves, I have to figure out who's top, who's bottom, right? That's very important. There's another situation that you could obtain. Something like a function does that, which is, it's not really a function per se. But there might be cases where you can be given something that looks like this. For example, a curve that looks like, example, this could be something like x equals y squared plus 1. Right? So that's like a sideways problem, right? Now, how you might think of that is you can sort of split the function in two, right? So there's going to be here this top curve. You can think of it as the function y equals the radical of x minus 1. Well, and then the bottom one, I could think of as y equals minus the radical. That's actually not the right curve. This would look more like because I shifted it up, so I have to change this. X equals something like y minus 3 squared plus 1 or something like that. Whatever, right? If I want this guy to be like at the 3, right? So something like a sideways parabola. But obviously here, it doesn't pass the vertical line test, so it's not a function technically. But because it's a parabola, I can sort of solve for it. I can take a positive radical and a negative radical and get my functions that way. So I can have something like here, I can think of the top function as x minus 1, take the square root, and then I add 3. And then the bottom one, I can think of the bottom function as y equals minus the radical of x minus 1 plus 3. Right? So sometimes you're given the top and bottom functions outright. Sometimes you can create them by splitting one function in two. The important part is, though, you should be able to see something as a top and as a bottom. Yeah.
If it gives you, if it says that the domain is from, like, for example, first example, if it says like g2 of x is less than or equal to y, which is less than or equal to g1 of x, but then you negate your value for your volume, or are you still trying to find volumes? Then you, if it's like in like calc 1, it would be like negative if you did that way.
What, you mean if you switch these? Yes, you'll negate the answer, but that's not sort of how
Not
we...
switch them there, switch them in the integral. So put g2 of x on the bottom. Put g2.
Yeah, you'll get the negative of what you should get.
So yeah, so that's like that. Did the answer then the negative, or would you still want the volume?
It depends on what's asked. Here I'm describing the region, right? Don't really put a context to it yet,
Okay.
right? But yeah, if I ask for volume, I mean positive volume. You're gonna, if it's negative, you have to.
And it's the same thing as if they overlap and you have to break it up.
Yeah, all that stuff still applies, right? Right here, I'm not doing a context. I'm looking at d. So I'm talking about, we're looking at something that looks like integral of d, f of x, y, dA, right? I'm talking about looking at the d only. When someone describes the region you're integrating over, if you notice this sort of relationship, where you can think of it as a top curve and a bottom curve and left constant and right constant, this is one way you can set the integral up. At the end of the day, this guy would go with this setup. Don't put a context to it yet. I'm telling you the mechanics of how to set it up. Don't worry about, it's a positive volume, negative volume. That comes later. Right now I'm telling you how to compute it. This is just the mechanics of how we set these things up. Here, so in the last example, my y equals positive radical x minus 1 plus 3, that's like my g2. And then the y equals the minus radical x minus 1 plus 3, that's the g1. Right? So basically here, we can set up the integral as go from a to b for the x, and go from g1 of x up to g2 of x for the y of f of x y, and I do dy dx. Again, remember that the x, these guys have to line up. Guys on the outside must go to guys on the outside, guys on the inside goes to guys on the inside. This here, you put the left constant. Up top, you put the right constant. Here, you put the bottom function. And up here, you put the top function. So not every time they're going to give you this. They're going to say, find this where D is the region described by, and they'll describe it to you, right? But when they describe it to you, what you have to do is you draw a picture. And from your picture, you can say, okay, this is on top, this is on bottom, that's on the left, that's on the right, this is how I'm going to set it up. So you can set it up this way. Your book calls this a type 1 region. I don't really care what the name is. You may also have a region like, this is the other flip side, the set of all points such that now my y value goes between two constants, say c and d, and my x value goes between two functions, h1 of y, h2 of y. Right? So in that case, your thing would look like this. So I can have two functions like this. This here is my h1 of y. This here is my h2 of y. Here's my c, here's my d. This is my region d. Right? Or I can look like again, I can have my two functions creating their own boundaries with their intersections. In which case this intersecting point will be the D, that intersecting point will be the C. This guy will be my H1 of Y, this guy will be my H2 of Y. Or I can do something like have a parabola in which, and let's say I wanted to cut it off here at D. In which case, I could split the parabola along the vertex, and I can talk about one half of the function and the other half. So I can talk about this guy here, this half as being the H2 of Y, and I can think of this guy over here as being the H1 of Y, and I might have the limits C and D here. Now the important thing you have to remember here is that you can consider this as a right curve and a left curve. And this would be a bottom constant and a top constant. So whenever you see a region or a region described to you, and when you draw it as a picture, you can sort of see, oh, well, there's a function on the right and there's a function on the left, and I can actually bound those by constants at the top and bottom. That is called a type 2 region. We don't care about what the name means, but the important part is the setting up the integral. The setup of the integral in this case, by describing this f of x, y to dA, you would set that guy up as c up to d, h1 of y to h2 of y, f of x, y, and now you do dx, dy. Outside, you always constants on the outside. Constants on outer integral. Always. Single variable functions on the second integral. Always. Right? Even though they might look like they're constants here, you have to think of them as functions. Right? They're single variable functions. Yeah.
You're setting up going from the right, the redness graph. Would you be integrating from and to the same function?
For this one?
Yeah.
No, one is going to have like a positive radical and a negative radical. They won't be exactly the same function. They'll differ by a sign somewhere usually when you split things in two. Right? Just as over there they differed by a sign. Right? This actual square root was different by a sign. Right? But the important part here, again, let me emphasize this. This here on the top I put the right curve. On the bottom I put the left curve. You have to know what's on left and right. Right? You hold up your how to your left. Hold your left hand. Whoever says the L. Alright, that's very important. Knowing left and right, top and bottom. Here you're going to put the bottom constant. Here you're going to put the top constant. Right? I'm just trying to let you know. Things might look complicated. The functions might be complicated. Everything might look really scary. At the end of the day, it's all about top, bottom, right, left. That's all you're doing at any given time. Right? Keep that in mind. That's very important. That's what's going to keep you from getting confused. You're like, oh my god, there's an exponential and there's a z squared in the exponential. Doesn't matter. Who's on top, who's on bottom, who's on left, who's on right. That is all that matters at any given time.
For the second example, they wouldn't even have to give you C and D, right? They could just say find where they're intersecting.
Yeah, they might say something like, integrate over the region bounded by the curves.
Yeah.
In which case, it depends on what the curves are doing up here. Like, they might intersect again,
And then
right?
it would need to be-
And then they would have to tell you. But if they never intersect again and they say bounded by, then yes, this should be clear. Right? But it sort of depends on the broader picture. What's going on. Okay. But again, constants on the outside, functions on the inside, and you have to set it up. If this is a dx dy, it means you need to have left, right, bottom, top. If it's a dy dx, you need to have bottom, top, left, right. Right? Always constants out here, always functions out there. I don't think we have much time left. Let's just do one example. We'll just do one example. I want you to set it up both ways. Not going to be terribly crazy. Set up the double integral of d of f of xy dA if d is the region in the xy plane bounded by y equals x and y equals x squared. Set up as dx dy and dy dx. Because I want you to compare the two. There are going to be time when you can do either or a mixture of the two. I guess I'll have to talk more about that next time, but for comparison, I want you to set this up both ways. Okay. So first of all, what does our region look like?
A parabola.
This is an x, this is y. We're going to draw y equals x squared, it's just a parabola. Y equals x, just a straight line through the origin. What's the region bounded by them? Just this part here, where it's going to intersect here and here. What are the intersecting points? 0 and 1, right? Again, it might be obvious here, but if they didn't tell you, how would you find the intersecting points?
Equal to 2.
Right, so you'd have intersecting points, you'd set them equal. That means if y equals x and y equals x squared, this means you want to set x equals x squared, in which case you get x squared minus x equals 0, x times x minus 1 equals 0, x equals 0, or x equals 1. Right? Here it's obvious, it's not always going to be obvious, sometimes you have to solve for it, this is how you would solve for it. Set them equal, solve for the values you need. Okay. Alright.
Set up the.
I actually want to set, this was the example I had before, but for emphasis, I want to actually change things slightly. Because I don't want you to think the x and y limits are always the same. Think of this as 2x, right? Where would those intersect? So this would be 2x, 2x, 2, 2. So this would be 2. Okay. Now what? So let's say I want to set up the dy dx setup. How do you think I'd write this integral? Right, so here I realize x is going to be my constants, right? Because the dx is on the outside. My x is going to be the constant, so it's going to be from 0 to 2. That's my constants. Then my y is going to go between functions. What are the functions on here?
The bottom one, which is the x squared.
This is what?
The x squared.
The x squared goes here, the 2x goes there, right? How do I know? In my picture, who is on the bottom? The parabola is on the bottom. Who's on the top? The straight line is on the top, right? This is the function y equals x squared. This is the function y equals x. This is bottom, that's top. Okay, so now if I'm writing this integral out, f of xy is going to be some random function that you're going to be given. I'm doing this as a dy dx. On the outside goes what? 0 and 2. On the inside, what goes here? X squared up to x, 2x, right? Left, right, bottom, top, constant function. Do I have space for the... Let's do it. I want you to be able to see the picture. Okay, now, if I were supposed to set this up as a dx dy integral, which in many cases I'll have the choice. Now what's going to happen? My y has to be the constants, right? So this was here the function. My y has to be the constants, and my x has to be the functions. So what are the constants for the y? 0 to 4, right? So the constant for the y, you have to figure out what's going on the y-axis. So that's when you have to map this across. When x is 2, this function y squared will actually give me 4. So the y constants are 0 to 4. The x... y over 2 to the square root of y. How do I know that that's how it goes in that order? Because now I'm looking at this object and I'm not looking at top to bottom. I'm like looking at who's on the left, who's on the right, right? So if I'm a little man trapped in this object and I look to my left, who am I going to be seeing? The line, right? If I look to my right, who am I going to be seeing? The parabola. Therefore, the line must be on the left, the parabola must be on the right, right? So I have to solve for the other guy. So I have y equals x squared. I solve for x, I get x equals radical y. If I have y equals 2x, I solve for x, I get x equals y over 2. On my left is the line, on my right is the parabola. Therefore, on my left is this, on my right is that. And then the limits would be set up. F of xy, dx, dy. On the outside, I would have 0, 4, y over 2 up to radical y, right? Bottom, top, left, right, constants, functions. Right? Once you have a y on the outside, it's bottom to top. X, left to right. The outer integral, always constants. Inner integral, always functions. Okay. We'll stop there. I have a little more to tell you, so no homework on Tuesday, but we'll have a quiz. Pass up your homework for today.